there are different views on this. I've never been afraid of speaking my opinion, and certainly my opinion is that no, actually they don't merge. Graphics remains a very, very highly parallel compute problem, embarrassingly parallel in the phraseology at the moment. You know, we do something on every vertex in the frame, we do something on every pixel in the frame. And we exploit this data level parallelism through thread level parallelism. What we've then built is a throughput computer. We've built a throughput CPU designed very much to maximize the throughput of computing on that device. And those throughput-orientated architectures and implementations will continue to be successful because of the reasons of performance and energy. Now, CPUs are almost certainly going to remain considerably easier to program. They're much more straightforward in the model of the CPU that they present to the programmer. I say model because, of course, under the hood, they're ridiculously complex devices these days, but we present an illusion, the CPU designers, we present this illusion that there's one instruction being executed at once and it proceeds in a sequential direction through your program. Of course, they don't do that anymore. I'm sorry if anyone didn't know that. I feel like the man who just said there's no such thing as Father Christmas. But really, that's the way it is these days. So I don't think so. At ARM, we've produced a new GPU, the Mali T604, and we've produced a new compute architecture for graphics and for GPU computing. We have a pipeline architecture illustrated in the bottom right-hand corner where we split it up and have different pipelines for different types of workload. We can scale this, we can put down more arithmetic pipes for everything that's required for very arithmetic intensive workloads. We also have texturing, which is very specific to graphics, where we can hide lots of memory latency. We're not in the 20 teraflops department yet of the 2020 devices being talked about from AMD, but we're getting, I have to tell you, a long way towards that. Even today, we're up around 68 gigaflops for a sort of device you'd find in a mobile phone, which is, you know, still pretty impressive in the 1 watt sort of territory for power consumption. We scale this up to 4 cores today, and we have a roadmap out through scaling it to much more significantly higher numbers. Memory bandwidth is power. This device, this GPU, consumes a bunch of power and dissipates power inside the GPU. It actually transpires that moving the data in and out of the device and the power dissipated in the DRAM and the memory controllers and all of the bus infrastructure is about the same amount of power. If we can reduce the amount of memory bandwidth we use, we can directly reduce power consumption. We can directly save on energy. And this is what this device is designed for. It's designed for efficient throughput computing. We will get the computational workload through this GPU in an efficient way. Of course, we support all of the usual APIs, both for graphics and also for GPU computing. Very much, you cannot get any distinction between AMD and ARM in our fulsome and enthusiastic support for open standards. Open standards are the way that you guys make money. And if you guys make money, we make money. It's as simple as that. If we can agree on open standards, we can drive forward without needless differentiation. But again, I kind of don't want to talk about the GPU. I want to talk about the system. It's all about the system, stupid. Complicated diagram, don't look at it too much, but there's lots and lots of bits in there, and there's lots and lots of data paths. The graphics, the GPU, at the top, in the middle, there's our graphics. There's some lovely CPUs over on the left-hand side, and there's an awful lot of interconnect to be had between those two. There's an awful lot of distributed MMU capability, so that we're all using the same page tables, we're all using the same unified memory architecture. We've been a unified memory architecture for 20 years. We believe it's the way to go. And we have a cache coherent interconnect, because in computer science we know that the offloading a piece of work from a CPU to a GPU or to any other compute accelerator, it's all about how small a device, how small a piece of work can I offload. And that relates to how much does it cost to offload that work. And directly related to the cost is your memory system architecture. If I need to flush a whole bunch of caches out to memory, it's going to be expensive. So it better be a really big piece of work to accelerate on the GPU to make up for that cost. The smaller that cost is of offloading the work from one device onto another, the easier we can move stuff backwards and forwards in the most power efficient format. And that's the game we need to play. We've got to be moving towards getting that computing done in the most power efficient place. So, you guys need to worry about moving data around in a cache coherent world. You guys need to be worried about the power that your computation costs. And unfortunately, some of this is coming your way.